Hello friends, welcome to E-Pathshala. My name is Indra Sen. I'm an assistant professor in the Department of Earth Sciences, Indian Institute of Technology, Kanpur. So today I will talk about phase diagrams and experimental petrology. So first let me explain you what phase diagrams are, what is experimental petrology. So to start, let me talk about experimental petrology. So this is actually a branch of petrology which simulates the crustal mantle conditions in your laboratory to understand the magma genesis and evolution on the Earth's interior. Now as you are all aware, magmas are basically what? Molten rocks, molten rocks in your interior of the Earth, and as soon as it comes up to the Earth's surface we call it as a lava. So it is very important for us to know what are the large scale processes that actually happens inside the Earth's interior. Now how do we know about Earth's interior processes? The best approach would be to actually look into samples, but do we have the capability to actually grab samples from a depth of say 5 kilometers or 10 kilometers from the interior of the Earth? No. So we have to depend on the lava that is actually outpoured on the Earth's surface, and from that we do various test analysis to actually infer what is happening at the Earth's interior. Or the other approach would be to look into direct rock samples from the interior of the Earth, something called mantle xenoliths. So xenoliths are basically broken rock fragments which usually the lava brings up to the surface. But still these are the ways to actually probe the Earth interior looking at samples. But the drawback of the approach is we cannot really go back to depth below 4 kilometers or 5 kilometers, because even the deepest mantle xenoliths won't actually come up to the surface. So then how do we know what actually exists in the interior of the Earth? Then that is why the experimental petrology comes into play. So as I said before, experimental petrology is the branch which actually simulates the Earth's crustal and deep mantle condition in your laboratory. So basically you are studying the Earth's interior right in your lab doing various experiments. So as I said, how do we probe Earth's interior? One way is to look at the lava which is actually on the Earth's surface, and from there we can actually infer what is there down in the Earth's interior. Or we look at mantle xenoliths, which are actually broken rock fragments which are brought up to the surface by the lava. But still in this way, although these are the mantle xenoliths are direct approach, but the lava is an indirect approach, we still cannot go really deeper into the Earth's interior. So the only way we need to look into it is through experimental petrology, where we actually simulates the Earth's crustal deep mantle conditions in your lab. So what do we do, and why it is important? Because these are also important because all the phase diagrams, and I will come to it what phase diagrams are, but all the experimental work lays the foundation of phase diagrams. So now let us look into what phase diagrams are, and then we will slowly look into the experimental petrology, why it is important, how it is done, how phase diagrams are constructed, where it is applied, and then finally I will look into the unary systems. So to talk about phases, so before even you understand what phases are, what you need to understand is the concept of a system, component and phases. So system is basically defined by us, the users. Say for example, the classroom where you are listening this, that can be treated as a system. System can be open system can be closed system. Say for example, if you shut all the doors and the windows of your classroom, that would act as a closed system. But whenever anyone open the door or the window, that becomes an open system. System is not scale dependent. For example, a crystal can be treated as a system, and all the atoms inside is basically its different components. So by this time I am sure that you understood what systems are again, and if you think that the entire Earth can be also treated as a system if you talk about the entire universe. So within system there are phases. Say for example, if you have chairs and tables inside your room, so these are the different phases. So first phase is your chair and the second phase is your table. So, within the component there are phases, and of course, the chairs and tables are made up of something, that is the chemical constituent, and that is its component. So, system, inside system there are phase, and inside phase there are components. So, when we talk about rock systems, for example, if you look at basalts. So, basalts are what? It is basically primarily made up of pyroxene and plagioclase. So, now if I talk about system, so basalt is your system, it is made up of plagioclase and pyroxenes, that is your different phases, and of course, the chemical composition of pyroxene and plagioclase, that would be your components. Say for example, in a system of phosphoride and silica. So, what is the formula for phosphoride? It is basically a magnesium silicate, correct? So, it is Mg2SiO4, and silicate is basically it is SiO2. So, out here how do we define components? So, as I said, it is Mg2SiO4 and SiO2. Remember, it is, so of course, it is, as you can see from the formula, it is actually made up of magnesium, silicon and oxygen, but that is not the way we define constituents, components. We define components as the minimum number of components that can actually explain your phase. So, for example, for in your phosphoride silica system, it is basically your MgO and SiO2 that will tell you about the system. So, that is also a very important thing, that you should understand, that the concept of system, the phase and the component. And the other thing you have to keep in mind is the phase rule. So, phase rule, if you have read into your books, that is great, but phase rule was basically first proposed by Dr. Gibbs in 1876 to 78. So, what actually it states? It actually states the relationship between the component phases and the variable, the temperature, the pressure that we just talked about. So, phase rule is basically, if you can take your paper and pencil, you can write down, it is F equal to C minus P plus 2. So, where F stands for the degree of freedom, C is your component, P is your number of phases and plus 2 are your intensive variables. It can be temperature, it can be pressure. So, for example, when you do your study at a fixed temperature, the formula reduces into F equal to C minus P plus 1. So, now let us slowly we will move into the different phase diagrams, the unary systems, which are actually made up of single component. So, as I said, phase diagrams, we talked about phases. Now, what are phase diagrams? Phase diagrams are basically nothing, it is the graphical representation of the different phases. So, it actually allows you to understand the different phase relationship in a pressure and temperature or a composition space. Now, how do we draw this phase diagram? And that is where your experimental works comes into play. So, just to review, I talked about the different definition of phases, component, system. We introduced you to the phase diagrams as well as experimental petrology. And I said that in only way to probe the interior of earth is actually to look into experimental petrology, because that is the way we can understand the various reactions that is happening deep down in the earth, which is actually inaccessible to us. Now, coming back to your lab, you actually, what experimental petrology does, as I said, you basically perform all these reactions inside a controlled environment. Now, depending on your nature or choice of project, you actually design your experiments. For example, if you want to study the reaction texture on the earth's surface, you use something called a gas furnace, where actually you go up to high temperature of like 50 degree to 1000 degrees Celsius, and you study the different chemical reactions, what happens. But whenever you would like to look into the lower part of the crust or even the upper part of the mantle, you need, of course, in addition to temperature, because you all know that as we go in the deep, as we go deep inside the earth, the temperature rises as well as the pressure rises. So, you have to simulate a condition where both your samples or your experimental starting material is actually subject to the same temperature and the same pressure when you are talking about the deep crustal or the mantle conditions. So that is why the instrument we use for studies at least to a depth from 0.3 GPa to 40 50 GPa, and remember 1 GPa is at least 30 1 GPa is 10 kilobar. So we use something called the piston cylinder. So out here on this figure what you see is actually a schematic drawing on the photograph of a end loaded piston cylinder. It is from Charles Clapham from University of Bristol. So you do not get into the details, but what it is usually done, this is your piston, there is the top piston and your bottom piston, and your samples are you are really working with small samples like few milligram or even less. So what you do is you take say you want to study the reaction of a basaltic melt with a different melt. So you take both the powder or basaltic powder and the alkalic powder or something, and you put it inside your capsule, and then you start putting pressure and as well as temperature, so that you subject that material to the desired pressure and temperature where you would like to probe, and mostly it is crustal or deeper mantle or upper mantle conditions, because we do not have direct physical, usually it is not a very common thing to have direct physical samples from such great depth. And then you take out this run, and of course then you look into the petrography of it, and then you do the probing to understand what sort of possible things and processes that could have happened deep down in the Earth's surface. So same way, using this sort of techniques, different experimental runs, what we do is we come up with phase diagrams. And again, if I repeat what phase diagrams are basically, it actually gives you the graphical representation or the graphical visualization of the stability of the different phases. Keep in mind that phase diagrams cannot tell you what are the possible phases that could come up in your system, but it actually gives you the stability field of each phase. So how do we draw the stability field of each phase? So we run our experiments, maybe it is a furnace, maybe it is a piston cylinder, again depending on where you want to study in the Earth's interior. And we run, say for example, what out here what you see, you have a mixture of two components out here, right? You remember components? So you have a component and you have a B component, and these are the various mixture of different. So you are adding, A is 100% here, A is 90, then B is 10. So these are the different mixtures of A and B component, and then what you did, you took your mixtures and then you put it in your piston cylinder, you ramp up the temperature to whatever you want, and of course you set the pressure, and then after that you observe the phases. Again remember, system, phases and component, I think that should be clear to you by this time, and if it is not, go back and listen to the introductory part of this lecture. So then you have a matrix where the temperature condition, the mixtures, and the possible phases. So then if you plot your mixtures on your A axis, so that would be your X axis. So X axis will have 100% A on one end and 100% B on the other end, and in between there would be all this mixture, and your Y axis you basically plot the temperature, and then if you plot the phases, you actually get a diagram which actually tells you what are the phases. Of course we know what are the phases, but it tells you the stability of the phases. When A will not be stable and when A will be stable, that diagram will tell you. Now do not think that phase diagrams are only used in igneous petrology, it has widespread application. For example, it is widely used by metallurgists, material scientists, material engineers to develop new alloys, to propose new material. So for example, this is a simple phase diagram. So again, if I say, you remember you have on your X axis, last time what we said, on your X axis you have two different mixture of A and B. So, out here you see the carbon weight percent on your x axis, and on your y axis you have temperature. So, same thing, this phase diagram was drawn based on experimental runs. So, they have conducted experiment at each of these grades, the small grids you see, and they came up with the different phases that were there, and then they came up with this diagram. So, what it says, it's the easiest way to read, you will see how phase changes happen. Say for example, you look at 5 weight percent of carbon and you look at 1000 degree Celsius. So, it is intersecting somewhere out here. So, it would be mostly austenite and cementite. Basically, these are the different forms of steel. And then if you come down, so from 1000 you keep your carbon weight percent constant, and if you come down to your you lower your temperature to 500 degree, you see you won't be getting the austenite, you will be you will start getting ferrite. So, based on this diagram, this is a very powerful graphical way of showing you what sort of phases that you would expect, and that can be your alloy, that can be a rock, or that can be any material. And these are all again drawn from the experimental runs. So, that is why experimental petrology is extremely important, because that forms the foundation of all your phase diagrams. Now, we talked about the phase rule. You remember I talked about phase rule is what? Basically, it was invented by Dr. Gibbs in 1876 to 78. It states the relationship between your component and phases, and the two is your intensive variables, that is your temperature and pressure. Now, out here what we see is, we have plotted temperature and on your x axis and your pressure and your y axis. So, out here this is basically nothing, it is a liquid, right, it is your water. Now, water, if you look at the how many phases of water you can think of. First one of course is your liquid water, then it is your gas, and then of course it can be ice. But remember, it is all being explained by a simple chemical formula, which is H2O. So, in this case you have only one single component, because remember the definition of component. The definition of component is the minimum number of chemical constituents which are required to explain your phase, and out here it is H2O, which actually describes all your phases. So, you have your gas, liquid, solid, all are made up of H2O, but they are of different phase. One is liquid, one is solid, and one in gaseous state. So, out here I will show you how you can apply your phase rule. So, again, so for example, let us look at the point C out here. Now, at C, what you see here, it is the liquid field, correct? So, your component is always 1 here, because it is a water system. Your phase out here is 1. So, 1 minus 1, that is 0, plus 2. So, your degree of freedom is basically 2. So, it actually represents the number of intensive variables that can be changed independently without the loss of the phases. That is what the degree of freedom means. Now, things will change as you move from this field, the field of C, and as you start moving, say for example, you are on this line. So, now let us look at the degree of variance on this particular line. So, again we go back to the same formula, F equal to C minus P plus 2. Now, out here when you are on the line, what you see, what are the components? Again, it is a water system, so the component is 1. Now, what are the phases? Now, here the phases are liquid as well as solid. So, from 1 minus 2 plus 2. So, you see the degree of freedom actually decreased by 1. Before at C it was 2. Now, as you move towards the line, the degree of freedom actually has decreased by 1, and the F is now 1. And now, when you actually move to the point A, now what is there in A? A has both gas, it has the gas, solid and the liquid phase. So, you have component, again remember it is just H2O. So, component is 1, phase is 3 because gas, liquid and solid. So, 1 minus 3 plus 2. So, now the degree of freedom decreases and it becomes 0, and that is your invariant point in a phase diagram. So, the line, again the line has what we said, it has a degree of freedom of 1, and that is what we call the univariant line. This means that two phases can occur only along a line where both phases are stable, because only along a line can one simultaneously vary P and T. So, anyway, I think this is clear. Same with point A. At the invariant point, that is A, as you can see, all the three phases can stay together. So, now let us talk about, so now I think by this time if I quickly review, I think it should be clear to you by now that what phase diagrams are, what are component, what are system, what are phases, how phase diagrams are constructed, what is its major application, what is its utility, what it can tells us, and always remember it cannot actually, it only tells you the phase relationship. It cannot, phase diagrams cannot predict the existing or a presence of a phase. It is just a graphical representation of different phases under a PT or a pressure temperature composition axis. So, now when we talk about phase diagrams, phase diagrams can be made up of a single component, it can be made up of two component, it can be made up of three component. The single component one we called it a unary system, what with the two component we call it as a bivariant system, and when you call with three component a ternary system. And of course, you can keep on going the increasing the number of components, and things becomes more and more complicated. So, in this module let us look at the simplest phase diagram, that is only with one component. A classic example would be your water system. As we discussed right now, water has a single component because all the different phases of water, the liquid, the gas and the ice, they can all be explained by the simple chemical formula H2O. So, it is a single component system. Or the other geological relevant system is your Al2SiO5, that is your andalusite, kyanite and sillimanite. So, these are the very simple univariant system that you should be aware of. So, out here what you see, sorry these things are not coming up because of some projection issue, but out here it is basically again a phase diagram, and these lines are basically your univariant lines, correct. What you plot on x axis is your temperature and on your y axis is your pressure. So, now if I say, please write it down, this field is your andalusite field and this field is your sillimanite field and this is your kyanite field. So, now what we can look into it, again apply the phase diagram to actually look at the degree of freedom. So, if we consider a component out, a field or point here, so what would be the degree of freedom there? The degree of freedom would be, you can calculate what is the phase rule, it is F equal to C minus P plus 2, component is 1 because it is a Al2SiO5 system. So, component is 1, phase is 1 and you have pressure and temperature. That means the degree of freedom is 2 and it is a divariant field. But similarly on the line it actually tells you the degree of freedom. If you calculate, if you apply the same formula, only the things what will change, that you will have two phases out here, that is your andalusite and sillimanite. So, two phases, the degree of freedom would be 1 and that would be your univariant line. Now, what would be the degree of freedom at I? At I, all the three phases are stable, that is andalusite, sillimanite and kyanite. Since all of them are stable, so you have three phases, one component and plus 2, so it is your 0. So now what this physically actually means, it actually all this, it's again this is the most simplest system you can think of. So what it actually tells you, if you have the temperature out here and you pressure out here and you look at any condition, right, and if you say my temperature or my temperature is constant, so temperature will be only constant on a vertical line. So that is the only thing which is changing is pressure. So by having say a temperature here constant, and if you just increase the pressure, your phase from here to here will change from Andalusite to kyanite, right. So this is the way you can actually predict what sort of phases that can actually coexist. So let me summarize what I have said so far. So we started with what are phase diagrams as well as experimental petrology. So again to revisit a little bit, so phase diagrams. So before phase diagram, let me say repeat what I said. So you have to understand the system, the definition of a system, phases and component. Again, systems are defined by us. So if you are hearing this inside your room, you can treat that room as a system, and it would be an open system if your doors and windows are open, but if the doors and windows are closed, that can be a closed system. And inside your system there would be different phases. So for example, if you are sitting on your chair, and that is your phase, and of course the chair would be made up of something that can be your that would be your component. So in a rock, say for example in a basalt is primarily made up of what? It is made up of plagioclase and pyroxene. So these are your phases, and of course the chemical constituent of your pyroxene and plagioclase, that would be your component. But just keep in mind one thing, that the components are the minimum number of components that would be required. Say for example in phosphoride silicate, if you look at the formula of phosphoride, it is Mg2SiO4 and silicate is SiO2. So out here you do not take the component as magnesium, silicon and oxygen, you just simply use MgO and SiO2. So out here the components would be 2. So then what we discussed that how phase diagrams are drawn, why they are important, what are they primarily used for. But before how phase diagrams are drawn, we discussed extensively about experimental petrology. So what is experimental petrology? Experimental petrology actually deals with recreating the environment in deep at high pressure and high temperature. And why you need to do that? Because you remember deep down on the earth, those samples are inaccessible. How do we probe deep earth? The two direct and the most indirect way is we look at the lava. So when the magmas are molten rocks, when they come up to the surface, we call it lava. So you can probe the lava, its chemical composition and everything, and then the indirectly you can infer what is happening deep down. But and the other direct way is when you look at mantle xenoliths. Mantle xenoliths are broken rock fragments which come to surface through the lava. But again, with that you cannot really go very deep down in the earth, say for example over 3 GPa or 5 GPa, 6 GPa, again 1 GPa is 10 kilobar. So for that you need experiments. So that means you recreate the conditions in your laboratory. If you need more information, I think the best you can look up the magma factory. You can search for magma factory, the Tokyo Institute of Technology, you will get more information. So that is the branch of experimental petrology. So remember all these phase diagrams that we draw, is basically the difference. It's a graphical representation of the stability field of the phases. And how we have drawn it? We have drawn it using these experiments. Now experiments, as I said, it really depends what is your goal. Experiments can happen in in ambient in pressure in the near atmosphere, where you only require the temperature, and then what we use simple gas furnaces. We can control the environment by putting different type of gases. Or if you are really interested in deep earth, for example in the upper mantle or lower mantle, we use an instrument called piston cylinder. So what you do, you take your sample inside the piston cylinder and you put pressure from top and the bottom, and you raise the temperature, and eventually you take out your experimental run and you see what are the different reactions that happen, what are the formation, deformation. But you remember one thing, the major problem of experimental petrology would be to scale up, because ultimately from a millimeter scale of experiments you really have to think hard that how do we scale up to understand large scale mantle and deep interior processes. But then we looked into, as I said, when we looked into the phase diagram, also remember phase diagrams only tells you about the stability field of the phases. It actually cannot tell you about the what sort of phases that can be present. So, the phase diagrams do not have that capacity. And then what we talked about, phase diagrams can be very complicated, and it can be a single system, made of a single component, a single component phase diagram, a binary system, a ternary system, even more than that. And then we just started with simple unary system, that is, it is made up of only one single component. And for example, we have used the water system, so that is H2O. H2O can happen in 3 different forms: water, ice and gas. So, you have 3 phases, and its one simple chemical formula is H2O, so it is one single component. And then we also looked into the kyanite, andalusite and sillimanite system. And I would like to conclude that don't even think that phase diagrams are only restricted to petrology or igneous petrology. It is extensively used in the metrology by the material scientists, developing different kinds of alloy. So, it has a widespread application. So, better you understand phase diagrams properly. So, thank you very much.